It is being recorded. So now let's do some problem that I am going to post in homework, and this the same thing that we have been practicing in the last class. I told you we have four quantum number, and if you see the last quantum number ms is equals to plus half or minus half, it is good. But if you see some other number there, then that set of quantum number is going to be false. Yeah. So if you see ms value is equals to 0 or ms value is equals to 1 or ms anything minus 1, that set of quantum number is wrong. Yeah. So ms cannot have other values than plus half or minus half. Make sense? So good. So if you see the number 2, number B in 38, number B, there is a ms is equals to 0, and that's clearly wrong. Yeah. So I'm going to post something like this in exam and in homework too. So another one in number A. So I think we already did that number A. So I just did the number B and I showed where that is wrong. So that's wrong. So in number A, you will see n is equals to 2. Like you have a big house that has a name number 2, like the house. You see that? It's the second argument. So we are talking, this is a neutron proton here, this is n is equals to 1, this is n equals to 2. It's just like the big house, right? So you can divide this house into how many parts? So that is the L, so 2 parts. So you can cut this into 2 parts, then give them 0 and 1, just like 0 and 1. Make sense? So that's what we have been doing, right? So this big n equals to 2 can be divided into 2. Now, this 0 cannot be cut into further. So 0 cannot be cut into further. So ml is equals to 0 for 0, 0 is 0. Now, I'm going to cut this L is equals to 1. Now I cut this L is equals to, sorry. So that L is equals to 1 can be cut to from minus 1, 0 to 1, 3 values. So I can cut this one into 3 parts. 1 part, 2 part, 3 part, and I can give 0 here, minus 1 here, plus 1. Just like the cutting the big house into tiny parts. Make sense? So this is the ml values is 0, minus 1, 0, and 1 is this one. So this 0, from this 0, this one is coming. From this one, these 3 are coming. Right? So I just, for this one, this 3 one, like this, there was a 1 here, and I cut this into 3 parts. And for the 0, I could not cut that 0, so that 0 is already 0 there. Yeah? Just a trick. Okay. Now, and I already told you for ms, either plus half or minus half. It cannot be other than minus half or plus half, right? So let's look at B. N is equals to 2. N is equals to 2. In number B, number A, it is giving n equals to 2. And he is saying he got that n equals to 2, and he got a number L is equals to 2. Is there L is equals to 2 somewhere here? No. So this is clearly wrong. L is equal to 2 cannot happen there. So you need to come with the set of the quantum number for n equals to 2 and look back whether that number is there or not. Yeah? L equals to 2 is wrong. Number A. Now I'm going to do number C. That I also posted that in a PowerPoint slide. So you can just probably look there too. So let's say n is equals to 3 here. N is equal to 3 here, just like the big house, right? 3. Now I'm going to cut that big house, and I'm going to give L the name L, and I need to start from the 0, right? 0, 1, 2, right? So the big house, the number 3 cell, you have the house name is 3, and somebody come here and cut into 3 parts and give the name 0, 1, and 2, just like that. Yeah. So third cell can be cut like this, and then LL. Now you are going to write. Right like this. So ml. So for this one, you cannot cut further. So 0 is 0. Yeah. From here, this comes 0. But from 1, the number 1 can be cut into 3 parts. Like this is minus 0. Sorry, minus 1. This one, I'm cutting this number 1, right? Minus 1, 0, and plus 1. I cut this 1 into 3 parts, right? Now I need to cut this 2 into from minus 2, minus 1, 0, plus 1, plus 2. You see, that's how I cut this room into 1, 2, 3, 4, 5 parts. I cut this number 1 numbered one room into -1, 0 into these three rooms, right? And but 0 cannot be cut. This 0 room cannot be cut into further smaller part. Just like the house, and imagine that there is a rooms in the house, and you start to cut by that room. Make sense? Good. Now, what it is saying is that in number 3, he gave n is equals to 3, and L is equals to 1, and ML is equals to -2, and MS is equals to a plus half. This is good. You see, MS is equal to plus half. This is good. So either half or plus half or minus half. This is good, right? And then n is equal to 3. There is no problem because this principal quantum number. That's a big house. That's already there, right? And then let's say L is equals to 1. Do I have a L is equal to 1 here? Of course, we have L equals to 1. For L equals to 3, I have 0, 1, and 2. These three rooms here, right? Now I have 1, so this is good. Now my job is to look here. This is good. You see, ML equals to -2. I have L is equals to 1. So look here. Look here. L is equal to 1, right? So from this number, which number is coming? Is this the set, or this is the set, or this is the set I'm coming there? From this one. I'm coming here, right? From 1, -1, 0, and +1. You see that? So this, if there was a -1 or 0 or +1, I'm good. But it is giving me that, oh, you got this room into this room, and you are going to mix this with this one. That's not possible. Make sense? Good? Good. So you see, so this, if is equal to L is equal to L, from that L is equal to L, these are the quantum number you can have. You cannot have from 1, this quantum number cannot come. From 2, only this number can. If there were 2, my answer is right. Right? Make sense? But since there is a 1, and he's saying, oh, from I got the 1 and I got the 2. So there is a room number like the 1, and he got that room into 3 parts. That should be -1, 0, and +1. You cannot get -2 there. So this is clearly wrong. So last time when I was practicing with you, I didn't track here. I just say, okay, I have a -2 here, so that must be true. That's not true. Yeah. So if you have got if there was a 2 here, then that should be true because you have a room that is named is 2, and then you could cut that from like a -2, -1, 0, +1, and +2. Then that would be good. Make sense? Sure. Imagine a house and you start to cut, yeah, and pick the corresponding values. That way, I think it's easier. So good. So that's wrong there. So you will see something like this in, I think we don't have a good duster here. I think this is better. All right, so let's see the next one. State which of the following orbitals cannot exist according to quantum theory. Let's talk about the 2s. Let's talk about the 2s. Can it exist or it cannot exist? What is the value of n? N is 2, right? N is equals to 2. Now there's a big house. Now we start to cut that into like this. So L is equals to, cut that into 0 and 1. So L value can only go up to 2, right? 0 and 1. It cannot go up to 2. It can have 2 values and smaller than 1. So you have to start from 0 and 1. Yeah? So 0 and 1. What is the name of this one? S. 0 is, the name of 0 is S. We call that SAR. And then this is a P. So you see that, is it 2S possible or not? Did you get the S here? Yes, you got it. So this is possible. Yeah? So you got this number 2 here, and you use your own idea. Okay, how many this house can be cut into? So 2 rooms, 0 and 1. So 0 is S and 1 is P. So that is possible. 2S is possible. Yeah? Confusing? It's okay, right? Now let's do another one. 2D. Is 2D possible or not? Is 2D possible or not? If somebody asks you, oh, I have a 2D orbital, is it right or wrong? So let's write it. So n is equal to what? 2, right? So I am going to just pick this number 2 here, n equals to 2. Now I'm going to cut this number 2 into, this is like the house. Now I'm going to cut into different room according to our rule, right? So this is like the house. House name number is 2. Now I'm going to cut it in such a way that I give the quantum number 0 and 1. 0 and 1, because I have n equals to 2. Now I need to write up to 1 only. I cannot go up to 2, right? So I cut this house into 2 and I give the name 0 and 1. Just like this, yeah? And then, can I write 2 here, or I cannot write here? We cannot write here 2 according to the rule. So if it is equals to 2, I can go only up to 1, right? Now I give the name here. So what is this one? This is called S, this is called P. Do I have D here? No, I don't have a D. So this is clearly wrong. Make sense? Good. So now let's do another. What is here? 2D. We cannot have 2D. Now, is there something I was reading? 2D. All right, 3P. Now let's talk about the 3P. Is possible or not possible? So n is equal to what? 3, right? N is equal to 3. Now, like a house, we have a house, and this house has a number 3. So they put this number into 3. Now I need to cut this house into many parts according to my rule. So my rule of cutting that house is like this: 0, 1, and 2. I cannot go up to 3. So I can cut that house into how many parts? 1, 2, 3, 3, only 3 parts. So this is 0, this is 1, this is 2. Like this, yeah? So that's my rule of cutting that house into smaller parts. Now, what's the name of this one? Yes, the name of this one is P. The name of this one is D. I have 3, good. I have P, 3 is good. So this is good. You see that? Everything is here. Now this 3P can exist. Yeah? Now, what do I have is 3F. Let's see 3F. 3F. So just like the n is equals to 3. Again, I have a big house that is named as 3. Now I need to cut this according to my rule and put the label there. So I need to cut this as 0, 1, and 2, right? I cannot go up to 3. Only I can go up to 1 less than what I have previous, right? That's a big number, and I need to be 1 less than that big number. Yeah. Now I'm going to write the number here: S, P, and D. Do I have a F here? No, I don't have a F here. So this 3F is clearly wrong. You cannot have 3F. Yeah. So that's what we are going to keep track of the numbers and orbitals. Now let's look at one more, and let's say 5F. So 5F. So 5F. So 5F. So you have a house. The house is very big, and the number of the house is 5, right? You need to cut this house into many parts according to your rule. So n is equals to 5, and then so the cutting of that house, my rule is I cannot go up to 5. I start 0 and I go up to less than 1 less than this number, right? So that is 0, 1, 2, 3, 4. You see, 0, 1, 2, 3, 4, right? So 0, 1, 2, 3, and I think I have 4. So something like this. Yeah. Now look here. Do I have 5? Yes, I have 5. Now give the name here: S, P, D, F, Z. Do I have a F value? Of course, I have F value here, 3, right? So this is possible. This is possible. See, it's just like how I teach my kid in home, like how to add numbers and how to subtract number by just drawing the lines. So I teach my kid like, okay, can you subtract from 5 to 2? So 5 to 2, so 1, 2, 3, 4, 5. Now he's going to cut 2 like this, and okay, 1, 2, 3. It's just like that they count like this way, you see. So if you, in future, if you take the this kind of the course, you will be exactly doing how I draw those lines and I cut 2. So they eliminate what is possible and what is not possible, and they figure out how many possibilities are there. Yeah. So now let's do one final one. 5S. Is it 5S possible or not? So again, I have a house number 5. Like this is 5th orbit, right? It's equal to, so just make the comparison. I say, okay, I have a house number 5, and just like that. So n is equals to 5, and then now I'm going to cut this house into different part according to my rule, right? So I can call that as 0, 1, 2, 3, 4. So you see, I can cut this house into 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5 part. 1, 2, 3, 4, 5 part, right? So now I give over here S, T, D, F, G. Do I have a S there? Of course I have a S. So this is possible. This is good. Yeah. So there is no possibility that 5S doesn't exist. The S is always existing quantum number. So this one, yes, that's this quantum number. Any orbital you go there, there is no possibility of not having S because this is the first sheet, right? So definitely it is always there. So that's how you are going to solve those problems. So good. So I think now we go to the. Do we have other here? When n is equals to 4, n is equals to 2, and ml is equals to -1, what type of orbital does this refer? It is saying that n is equals to 4, I mean 28, n is equals to 4, n is equals to 2, and ml is equals to -1. So to name this orbital, you don't have to go here. You don't have to cut further here because this is coming from this one, and this name is already kind of merged in this name. Like just like this is a father, this is a father, this is a father, and this is the father's last name, and this the son, and this is the son's last name is same as the father's last name, right? So you don't have there to name the orbital. So you just go up to here. So just like the grandfather and father, you don't have to go to the children to give the name of the orbital. Yeah. So it's just like that. So this is 4. And what is the number of this? L is equals to 2 is what is the name this one? So if you have L equal to 0, 1, 2, you are going to give S, P, D, right? Yeah, but what he give is L equals to 2, right? So what is the name of L equals to 2? To D, right? So the D. So that is 4 is 4, equals to 2 is D. So we are talking about the 4D. You don't have to go there. So we have 5D orbital, dx, dx, dxy, dxz, dx square, y square, dz square. Out of those 5, this is 1. So this is the child of this one. So this guy has many child, and out of those, this is the one child. So you don't have to give the last name to that one, just like that. Yeah. So as long as you have the first one and the second one, then you can easily name what orbital is there. You don't have to go here. Yeah. Make sense? Good. Now, how many orbitals occur in n equals to 5? That I already talked in the in previous class. So you have n equals to 5, meaning that you have the fifth orbit. So this is neutron proton here, the first orbit, second orbit, third orbit, fourth orbit, and you have a fifth orbit like this, right? The fifth orbit. We are talking about the fifth orbit. So how many sheets it can be cut into tiny sheet? The maximum possible of the sheet I can cut this into, right? That's the question is. So it's just like the big house you have and the number of the house. Somebody give the number, this house is 5. So how many part, the maximum part I can cut this into, right? So that's the question. So I already told you n is equals to n square gives you the number of the maximum tiny sheet. That's 5 square equals to 25, right? That's what we talked in the last class. Make sense? So if you are given is n is equals to 1, you cannot cut this house into further smaller. N equals to 1 and n square equals to 1, right? And if n is equals to 2, so you have a number 2. So this is number 1. Now this is number 2. This house can be cut into further, like n equals to 0 and 1, right? And then we get 0 can be divided further 0, and 1 can be divided to -1, 0, and +1. That you would get 4. So n square equals to 4, right? So second orbit can be cut into maximum 4 part. Third orbit can be cut into maximum 9 part, and fourth orbit can maximum we can cut into 16 part, and the fifth orbit can we can cut up to 25 parts. Make sense? So that's the question. Good. Now, good. And if you have to name that, that's okay. So how many orbitals occur in F sub cell? So let's say how many orbitals occur in F sub cell. So take the F sub cell. So this is just to move the head. So F sub cell. So let's say this is F sub cell, right? So now write like this: L equals to 0, 1, 2, 3. So 4 like this, right? Like this. Yeah, this is the naming, right? So 0 is S, this is P, this is D, this is F, this is Z, right? And if there is a 5, maybe H, but so far people have not gone to H, so they are only up to Z. So they are looking if they can go to H. Yeah. So up to Z. So F. Now look F. So L is equals to, I have 3, right? So L means L, I have 3, right? Now my job is to cut this into a smaller part according to my rule, right? So ML is the child one. So L is the father, like the father, and ML is the child of that one, right? Now I'm going to cut that into smaller part according to my rule. So my rule is I start from -3, -2, -1, 0, +1, and +2, and +3. See that? So how many orbital, small orbital I can cut that F into? 1, 2, 3, 4, 5, 6, 7. Yeah, make sense? Good. So that was the question there. Now let's look at 29. So I think we are really trying to be expert in quantum number assignment. So now let's look this one, 29. A possible excited state of the hydrogen atom has the electron in 4p orbital. So normally, in normal situation, hydrogen is always in the first orbit. So this is a nucleus. Hydrogen is always in the first orbit, and we call that is a ground state, right? So if it is in first orbit, that's a ground state. Now, if you give the energy, there are many orbits, billions of orbits, infinite, like this, right? And then after this electron pick some energy and jump up to fourth orbit. 1, 2, 3, 4. It already jumped there. So that's called the excited state. Yeah. So excited state. So it is saying that the orbit is in the electron is in 4p. There are many states in that fourth orbit. There is a 4, there is a S, there is a P, there is a F, right? So there are many states, and out of those states, the electron is sitting in the P seat. Yeah. So one of those states, P seat. Now he is asking calculate all the quantum number possible for that electron. Now let's say so N is 4. Yeah. N is 4. Like there is a big house in the fourth house. It is in the fourth house. It's a address. The quantum number is just the electron's address where it is living. Yeah, just like I am in United States, and then I live in the Wisconsin, and then I come to the Eau Claire, and then I come to the University of Wisconsin Eau Claire, and then if it's just the address of the electron we are talking. Now N equals to 4. Now give the L value. So what is it? So write the L value: 0, 1, 2, 3. You can go up to only 3 from 4, 0, 1, 2, 3, right? Now this is P, this is D, this is F. So he's asking me for P, not S, not D, not F. So he's not asking this number. He's just asking the P, right? For P. So I'm going to pick this P here. So I don't pick this one. I don't pick this one. I don't pick this one because he asked me P. So P's name is 1, right? Now I'm going to write the ML value. So what is the rule of cutting this L into? From minus that number to plus that number, right? Yeah. So I'm going to write like this. So minus, this is the L is the 1, then -1, 0, and +1. So that's the all possible quantum number for the 4p. Yeah. So 4. So I could write N is equals to 4, L is equals to -1, 0, and +1. Sorry. This is not L. So this L is equals to 1 and ML is equals to -1, 0, and +1. Like this. So that's the address of this 4p electron. Yeah. Could be that maybe it's this one or this one or this one. I don't know where that is. Yeah. Because here I will have 3. This L1 can be divided into 3 parts. So that could be this one, that could be this one, or that could be in here. So where it is, I can say here. Maybe possibly that electron is here, possibly that electron may be with this seat, possibly that electron may be with this seat, right? I can say where it is. Yeah. Good. Alrighty. So I think we are done to the chapter 6. Now let's go to the chapter 7. Yeah, I want to start chapter 7. So this concept, we just take this concept to the chapter 4 and continue there. Yeah, the same concept. A little bit bigger. So this concept This concept, no matter where you go, this is the same thing always. Unless you're taking that Schrodinger wave equation and solving yourself, I don't think much of the people want to do something like that. There are not much job in everyday life, so I don't think people really want to do equation solving job these days. You see, so but to take the classes, when you take the course, all this you are going to take everything in the higher level, yeah. Unless you really do the research and take your own equation and start to solve, that's the only difference. Other thing is the same. So this is the maximum thing I learned. So that is what I am giving to you. Yeah. So I don't know much more than this one here. All right. So now we did that. Now in number 7, chapter 7. We started chapter 7. Chapter 7. So the same thing. So previously we said that one electron, to completely define the address of one electron, it needs to have a 4 quantum number, right? So if the electron is in first orbit, so I already told you L can be 0, cannot go up to 1, right? 0. So the address of this electron is 1s. So it is in the principal quantum number. This is in the first orbit, and that first orbit cannot be divided further, so that is already there. Yeah, so that's already there. So that's the address of that electron. And then if you want to write this L equal to 0 in ml, so that is going to be -0 to +0, right? So -0 +0 doesn't have any meaning, so we just write 0, right? And then now we need to go to the ms, the spin quantum number. Suppose in the first orbit there are 2 electrons, so this is 1 electron and this is 1 electron, right? How many electrons I have here? Maybe 2 electrons. So if it is a hydrogen, there is only 1 electron. But if it is a helium, there are 2 electrons in the first orbit. Yeah. So it can have 1 or it can have 2 in the first orbit. Now you see, if you give this, if you give +½ to both one, you cannot differentiate this one. So imagine that the same number, the n equals to 1 for this one is 1. And L equal to 0, the same thing. ML equal to 0, the same thing for this one. This 3 number is same thing for this one. Now we need to differentiate here. So if this number is, you give the name for this one is +½, for this one you are going -½ You see? So 2 electron cannot have 4 values. If 4 same values. If the electron, this 2 electron has same 4 values like this, ms is equal to +½ You see, this is also +½ this is also +½ right? If you give like this one, this electron and this electron is exactly the same electron. That cannot be possible. Can 2 electrons be the same electron? That cannot be possible. Electron name may be A, another electron name may be B, right? So 2 electrons cannot have the same exact address or the identity. So if you give +½ to this one, you are going to give this to the -½ to another one. So if you have 2 electrons there in the same seat, yeah. Suppose 2 things are sitting in the same seat here, exactly identical, and let's say this is a one, this is a A, and this is also A. So this is, if you give the name A and you give the name A in the same seat, you are not differentiating the 2 people here. So if that is the case, the A has another replica, and then he is sitting by you, right? So another person must be like the B, right? So one person cannot duplicate and sit close to its own like that, yeah. So if the one electron is A, another electron must be B. So that means the ms is +½ which is like A, ms is -½ which is like the B, yeah. So the 2 electron cannot have. So all electron in an atom should be given 4 quantum number to specify their identity. And if 2 electrons are in the same seat, exact same seat, and then one must have a +½ another must have -½ we cannot give +½ to both or -½ to both. If you give the same number, the identity of the electron is the same. The identity of the 2 electron is same. Yeah? Good. All right. So now, they did that, and they give a rule here. It's a very important rule. It looks simple, but it's really, really important. Yeah. So The name of the rule is the no more than 2 electrons. So they give the rule here. No more than 2 electrons can occupy the same orbital, and if there are 2 electrons in the same orbital, they must have the opposite spin. So let's start that. So you have a one S. Suppose you have a S orbital, right? So I told you S orbital look like this, right? Like the golf ball, right? So S orbital cannot have more than 2 electrons. It can have either 1 electron is jumping around, or there are 2 electrons they are jumping around. Yeah. So one orbital cannot have more than 2 electrons. Maximum one orbital can have is 2 electrons. Now, how about the p? So how many p orbital I have? We have 3p orbitals. One is like this, another is like this, another is like this. So yesterday we talked about this one. So p orbital have three form. So this orbital either can have 1 or can have 2 electrons, but cannot have more than 2 electrons. The same here. This orbital can have 1 electron or 2 electrons, but it cannot have more than 2 electrons. The same here. So if I combine this form of this one, so S orbital can only have two electrons. But how many p orbital I have? This is p, this is p, this is p. So this is pz, this is py, this is px. So this can hold 2 electrons. So this can hold 2 electrons. This can hold 2 electrons. So but I don't want to say px, py, and pz. I just want to say p, right? So that means how many? 2, 4, 6. So p orbital can have 6 electrons. Why? Because this can hold 2, this can hold 2, this can hold 2. So we can combine them and then say p orbital can have maximum of 6 electrons. But if you talk only one orbital, like the px orbital or py orbital or pz orbital, it cannot have more than 2. So remember that, yeah. So in later on when we do the electronic configuration, we will write the p6. Where does this p6 comes? We read that p can have only 2 electrons. Where? How can you put 6 electrons here? Yeah. So there might be confused there, but I'm just saying that there are 3 p's and 2 plus 2 plus 2, then it can have. So these 3 p's can have maximum 6. Yeah. Good. So p can have maximum 6. Why? Because I have 3p orbitals, and each orbital, each p can have maximum 2, and then 2 plus 2 plus 2. Make sense? Good. Now, and so each orbital can have either d or f or whatever that is. So if you talk about the d, so d orbital can be divided in how many parts? So d is like s, like this, s p d. This is 0, this is 1, this is 2. So this d orbital can be divided into how many parts? -2, -1, 0, 1, plus 2. You see how many parts I divided? 1, 2, 3, 4, 5 orbital, right? So the d orbital can be divided into 5 orbitals, and each of these orbitals can hold only 2 electrons. So this hold 2 electrons, this hold 2 electrons, this hold 2 electrons, this hold 2 electrons, this hold 2 electrons. So 2, 4, 6, 8, 10. So how many maximum electron a d orbital can have? 10, maximum 10, because there are 5 d orbital, and each seat it can hold 2 electrons. Make sense? Good. So later on, when we are doing this, we will write the d10. How does this d10 come? Because we have this d is divided into five seats, and each of those 5 can hold 2 electrons and give hold the 10 electrons. Make sense? Good. So good. So you read it. No more than 2 electrons can occupy the same orbital. In one orbital, if there is talking about the one orbital, the maximum possible electron in one orbital is only 2. Yeah. Good. And then if there are 2 electrons in the same orbital, suppose this is the s orbital. S orbital, it can have 1 electron or 2 electrons. So if it is a 1 electron, no problem, just free, right? Just like the roommate. So if you have a roommate, you need to adjust yourself, right? But if you can rent your own apartment, you can whatever you like in your apartment, right? Just like that. So this is a 1 electron. You don't have to worry. Whatever it is doing. Let's say we have 2 electrons here. Now there is a special way they need to sit so that they don't disturb each other. So this one, say, okay, I'm going to rotate to the clockwise. So it rotates to the clockwise. and we say that that's a plus half. Yeah, and then this is going to say, okay, I'm going to rotate the other way so that you don't get disturbed. So that is, and we give them minus half. Make sense? It's just like the roommate. So if you have a lot, it's good, right? Whatever you like, you can do it. But if you two person are in the same one is going to behave one way and another is going to behave another way, so that they don't interfere each other that much. Make sense? Good. So they must have the opposite spin, meaning that if there are two, so I just talk about the s orbital. Now I can talk this same thing in the p orbital. So let's say I have a p orbital, I have one electron, doesn't matter. So maybe it's spinning clockwise or anti-clockwise, I don't care. So, but if there is another electron, now I have two electron, this is spinning this way and this is spinning this way. So this has minus half, this has minus half, and this is plus half. That's how they give the number. So one was spinning this way. So they say, okay, if you are spinning the anti-clockwise, so I give the name half, minus half. And if you are spinning this electron spinning to the clockwise, I give the number plus half. Yeah. So the rule is orbital cannot have more than one electron. Sorry, more than two electrons. And if there are two electrons, they are not identical. One is spinning the right way, another is spinning the another way. Yeah. Make sense? So this is very important rule, and this rule is called Pauli's exclusion principle. Pauli's exclusion principle. So this is a German guy, and so I used to work in Germany for 1 year, and there I met many name. They asked him Pauli. So this guy gave this rule. Yeah. So Pauli's exclusion principle. What is the Pauli's exclusion principle? So one orbital can have maximum 2 electrons, and if there are 2 electrons, one is going to spin the clockwise, another is going to spin the anti-clockwise. Yeah. So that's the Pauli's exclusion principle. So another one. So Pauli's exclusion. We are good with the Pauli's exclusion principle here. Now, how much time? I have 37. I still have some time. So let's talk this one. Now, how to you see, atom is very complicated. If you have a hydrogen atom, it's very simple. But once you talk about the bigger atom, it's very, very complicated, right? So, for example, I have a hydrogen atom here, and this is neutron proton, and there is one electron. Very simple atom. So everybody want to study this because it's the simplest one, and everybody like to study this hydrogen. Yeah? But how about the helium? So you see, now this is a very simple atom. Now I talk about the helium. You see, hydrogen, helium has a 2 proton here and 2 neutron also, and that's a 2 electron. Now these things start to be complicated, right? Now let's talk about the lithium. Lithium. So now here is a 1 electron. There is 2 electron in the first orbit, and the second one is there. Now you said 1, 2, 3. Now even complicated. Think about the uranium 292, uranium 292 or 293. How many electrons it has? 292 electrons. Who knows what these electrons are doing in that crowded space, right? Maybe some are pushing, pulling, kicking out. Maybe all possibilities going on there, right? So the scientists, those who were working this one, and they come with the idea. So let's make those electrons behave a certain way. Yeah. So they say like this. So they give a rule like this. So this is very important. Yeah. So this is very important. 1s, 2s, 2p, 3s, 3p, 4s, 3g, 4p, 5s. You can write whatever later. So this is the order. If you have a 1 electron, this is going to sit with the 1s. If there are 2 electrons, they are also going to sit with the 1s. Why? Because one orbital can have maximum of 2 electrons, right? Now let's say you have a 3 electrons. So 3 electrons. Now how do I fill in that atom? Where are those electrons? So okay, I'm going to put 2 electrons here because this can hold 2 electrons. The one orbital can hold 2 electrons, right? Maximum according to the Pauli's exclusion principle. Now I still have one more electron left, right? So where should I put that electron? Now I'm going to put electron there. Yeah. So that's how we fill the electron. Now, let's say I have 4 electrons here. 4 electrons. Now, 2 electrons I'm going to put here. Where should I put the another remaining 2 electrons? Here. 2 electrons in 2s, second orbit, and then that spherical space of the second orbit. Yeah. Now, let's say I have 5 electrons here. So out of 5, I put 2 here, and I put 2 here. 4. 4 are already gone. So where should I put the 5th electron? Here. 5th. Make sense? That's how you need to put. Now, I have a 6 electron now. I have 6 electrons. Where should I put? So 2 I put there, 2 I put there, 4. Now I put 2 here, 6 electrons. Because p electron, I already told you, p electron can have how many electrons? 6. Because although we just see the one orbital is a p, this has a free seat it has. So px, py, pz. So I can put 6 up to 6 here. Yeah, because this p is divided already into 3, and they don't write because if they start to write the px, py, pz, the writing becomes complicated. So they don't write px, py, pz. Yeah. So this is 6 electrons. So 2, 4, 6. Suppose I have an atom that has 7 electrons. How do I put that? So 2 I put here, 2 I put here, 4. Now I am left with a 3. So I put it 3. Can I put it 3 here? Yes, of course I can put, because that p can hold 6, because I have there 3 seats. Px orbital, py orbital, pz orbital. There are 3 seats. So it can hold 2, it can hold 2, it can hold 2. You see that? So they can hold 3, right? So this the p is px, py, pz, that can hold 6 electrons. And since we didn't write px, py, pz, we just write p here. So I can put up to 6 electrons there. Easy? Makes sense? So in p you can put maximum 6 electrons. Now, how about I have an atom that has 8 electrons, just like that. Look the periodic table, and what is the number of that atom, right? Atomic number. So 7. 7 is what? 8 is what? Oxygen, right? If you look at the periodic table I put there's a number, 8 is oxygen. So what does the electron look like in oxygen? So 2, 4, because they have 8 electrons, 2, 4. So I'm going to put 4 here. 2, 2, 4. These are all empty spaces. This space exists there, but we don't. They do nothing. Just like the empty spaces. Yeah. Good. Now let's do. So and what I'm teaching is really important. Yeah. So if you in future if you take chemistry, it's really important. Yeah. Now I am. Let's say 9th atom is what? Fluorine. Look the periodic table, and fluorine is 9 atomic number, so it has 9 electrons. Now 2, 4, already 4 is gone. Now the 5 I'm going to put it here. So fluorine look like this. Yeah. Now let's talk about the neon. So neon. The neon in periodic table, it is 10. So 2 I put here, 2 I put here, so I can put up to 6 here. So now I'm done. You see, now the neon has already 6, and when you have a 6, the element behaves as it is inert. So neon gas doesn't react easily. Yeah, so that's the inert. Now we are done with the. Now let's talk about the after neon. What is there? Sodium. In 11, number 11, this is sodium, right? Look at the periodic table. 11. I'm done here. You see, I'm done, right? So p orbital cannot have more than 6 because p orbital has 3 seats. Px, py, pz. Each of that can have 2, 2, 2. So 2, 4 already filled, right? One orbital can more than two people. Yeah, good. Now I'm going to fill 11 here. So 2 I already put here. 4, 6, 4 is 10. Now I have one more, so I put it here. Yeah, makes sense. 11. Now after sodium, what do we have? We have magnesium. Magnesium is 12, right? Look at the periodic table. Magnesium is 12. Magnesium has 12 electrons. So 2, 4, 6, 4, 10. I have 2 more left, so I'm going to put it here. 3s2 for magnesium. So the magnesium has 2 valencies, so we can predict a lot of things from this electronic configuration. Yeah. So magnesium. So what else? So after magnesium, maybe aluminum. Now aluminum is number 13, right? Look, 13. So 2, you put 2, 4, 6, 4, 10 to 12. You cannot put another electron in S because S is only one orbital, so you cannot have more than 2 electrons, right? Yeah. So another electron I need to put here. So 3, 1. So that's for the aluminum. Yeah, so I might give something like this. Okay, I give this part, I just type this part in that canvas, and I ask you, what is the configuration of this represent? You are going to say aluminum, right? Because 2, 4, 6, 4, 6, 10, 12, 13. So 13 meaning that's aluminum. Just go to the periodic table and look what number is that. Yeah, it's confusing. It's confusing, but it's okay, right? You need to practice. Yeah, I practice so many years, so I know. But you need to practice. You're just starting, so good. Now, let's see another one here. So maybe after aluminum, you may say. So sometimes, so they write this as this one. So you see that this is a complete. So if you just write this one, this is a neon, right? 2, 4, 2, 4, 6, 10, right? That's what is a neon if you look that one. So sometimes they write like this. So neon. So after this one, they don't want to write this one. So they just write, okay, I already know what is going on here, neon, and they just write 3s2, 3p1. They also write like this way. Make sense? So after neon, so this is, if you look neon was in number 10. So 2, 4, 6, 10. So that was the inside orbital. So this is, okay, this one is a neon. I already know up to this part, and on the outside I'm going to write this. So either you write this way or this way is the same thing. Yeah. Now, yeah, we studied too much thing here. Now I'm going to, you just fill according to the rule. So maximum in P, write up to, you can write up to 6. In S, you can only write up to. Now I'm going to practice one, and it's really important. Yeah. So that I put that in. I think in the slide number 7. So this is really important. Yeah, you will see this kind of thing a lot. So I'm going to write copper. Copper. Look at the periodic table. There are 29 electrons. So we have 3 minutes. Let's finish this one. So you are just going to write as 1s, 2s, 2p, 3s, 3p, 4s, 3d, 3d, something like that. There is something like that. So this is the same thing. Always, this order is always same. I will tell you later why this order is always same. Yeah. So always you are going to write, no matter where, 1s, 2s, 2p, 3s, 3p, 4s, 3d. Now I'm going to fill this 29 electron here. So the first one I put 2 because that's S, and S is only 1. I'm going to put 2 here. P maximum 6, and S can hold only 2. P can hold 6. S can hold 2. And how many electrons I already put? 2, 4, 10, 12, 18, 20, now 29, right? Yeah, that's the rule, right? Filling. Make sense? So S can have only 2, P can have maximum 6, D can have maximum 10. So that's the rule, right? So just keep filling. But this is, when you do the experiment, this is not true. That's how we feel. So what they say is that, so D, try to have either half is good or full is good. You see, either half is good, HLF half, either half is good or full is good. So something else is not good. Yeah. So they try to be like that. So what they do is, so the S orbital is going to say to this D orbital, okay, I want to be half, only one, right? And I'm going to give you one of my electron to you so that you become full. This is the rule. There is not much thing, something like this in chemistry. There is a two thing. One is a chromium, one is a copper, and I just showed you the copper. Yeah. So yes, said according to rule, it was say 2 and 9, and I told you either half is good or full is good. So if this gives 1 to this guy, this is going to 10. So this is good, very good. He's very happy, and this is half. Okay, I'm good with the half. So this is half because S can have maximum 2. 1 is a half, right? This is the rule. Crazy idea, right? Who could think something like this? It's a crazy idea. All right, so I think we stop here. Thank you, everyone there.